going to look at a technique of partial fractions. So it's sort of a mixture of it's in the polynomials topic, but it's also in the integration topic, this idea of partial fractions. So what it is when we integrate and we've got some polynomial on top of another polynomial, how we decompose this into its original fractions. It's sort of like the reverse of adding algebraic fractions. So if the degree of the numerator is greater than the degree of the divisor, well, the first thing you do is perform your polynomial division. Okay? Similar to when we were graphing, and then that way it works out your oblique or your horizontal asymptote. If it's less than, then we can factorise the denominator. Okay? We get into its individual factors. And remember, from polynomials we saw, every polynomial can be factorised down to a mixture of quadratic and linear factors. So if you have got a linear factor in the denominator, then we're going to create a fraction with that in the denominator. And we just put a constant on top. So a over x minus a, and if there was another one, we put b over x minus, and so on, and so on. Now, if you have a multiple one, so maybe it's not just to the power of 1, it's the power of something else, you write down a fraction for each of the powers. So if it was a cubic, then I'd end up with 3 fractions. A over x minus a, b over x minus a squared, c over x minus a cubed. So whatever the power is, that many fractions is what we're going to create. Now if it is a quadratic factor, which we can't then go and factorise, then we put a linear function on top rather than a constant. So ax plus b. That's the basic idea, and that's how we decompose it down. So if I want to integrate x squared on x plus 1, well, the order is greater than the numerator. Sorry, than the denominator, I should say. So we'll do our polynomial division. We'll get x with remainder there of minus x, so we can keep going. X into minus x is negative 1. Leaves me with a remainder of 1. So I can rewrite my fraction as x minus 1 plus 1 on x plus 1. In this case, there's no work to be done because we just have one linear factor. I can integrate everything that's there. So I don't need to do anything more to the actual function itself. So now I'll just integrate. X goes to half x squared, minus 1 will go to x, and of course the fraction is a log function. So we would like them to all be that easy, of course. This one, a little bit more work. I don't have to do a polynomial division because I've got a constant on top, but I do need to factorise the denominator. So I've got x and I've got x minus 1. We want to break that back into the addition of 2 fractions. So one fraction will be a over x, the other fraction will be b over x minus 1. And we know that when we add these things together, we get 3 over x minus 1. Now, there are different ways of finding these constants. Probably the easiest way is to multiply everything by the x minus 1, and it gets rid of the fractions. And so I now have a new statement, a outside x minus 1 plus bx equals 3, and I just use clever substitution of x to find the values. So if I substitute in x equals 0, the b disappears, and I simply now have a statement that says minus a is equal to 3, a is negative 3. And then I can do a similar thing to find b. If I substitute in x equals 1, then the first bit disappears and I just get b equals 3. So I have my a and b. I now know I can rewrite this single fraction as the sum of 2 fractions, minus 3 on x and 3 on x minus 1. Both of those will be log functions when we integrate. Now, because the coefficient is the same, not worrying about the sign, of course, they're both 3 logs, I think I'll use my log laws to bring them all into one log. So we get 3 log x minus 1 over x, plus, of course, a constant. Okay, the numerator is a linear function. The bottom is a quadratic. So we don't have to do a division, but we're going to try and factorise the bottom. It does factorise x minus 5, x plus 2. So again, I will create 2 fractions, a on x minus 5 and b on x plus 2, multiply, get rid of the fractions, and I can do a similar idea to what I just did. Clever choice of values for x. So x is negative 2, I get b is negative 3/7. and x is equal to 5, I'll get a is equal to 10 sevenths. So I can go back, and there's my new integral, 10 over 7 lots of x minus 5 minus 3 over 7 lots of x plus 7. Again, I've just got log functions. So 10 sevenths the log of x minus 5 minus 3 sevenths. I'm not going to bother to put this all into 1. I could do it, of course, by bringing the 10 in as the power and the 3 in as the power. Then they both have a coefficient of 1/7, but I'm not going to worry about it. I usually only bring them in if those coefficients are the same. Cubic. And that can also be factorised, but this time we get a quadratic that can't be factorised. So I'll set up my fractions. For the linear factor, I've got a over x, but for my quadratic one, I've got bx plus c. Multiply to get rid of the fractions. Now, I can, again, use clever choice of pronumeral. If I make x equals 0, then I can get a straight away. Now, there's nothing that says I'm restricted to real numbers. So now, to get rid of the a, I'm going to substitute in I. And then the x squared plus 1 disappears. And I now have, on the other side, minus b plus ci, because of course I've got bi plus c all times I. And that equals 1. But the real part must equal the real part, and the imaginary part must equal the imaginary part. So b is -1, and c is 0. So now I can go back, and there's my new integral, 1 on x minus x on x squared plus 1. Yet again, we've got two log functions. So the first one's log of x, the second one becomes minus a half log of x squared plus 1. So an advantage of knowing about complex numbers now, we can use imaginary numbers to make that substitution a bit easier. Okay, now with this one in the denominator, I've got a double root of the x plus 1, and I've got a quadratic that doesn't factorise. So this time I need two fractions for the double root. So one is a on x plus 1, the next one is b on x plus 1 squared, and then for the quadratic, I need to put a linear function on top, so cx plus d. Multiply that one out, and I have this wonderful expression to try and find a, b, c, and d. But again, clever use of pronumerals will make this easier. First what I'm going to do is -1, so the a disappears. The cx plus d disappears as well, leaving me with just b is -1/2. So I've got b. I'm going to use I, because that will get rid of my x squared plus 1s. Does give me something a little bit more interesting to expand out, of course, because I've got I plus 1 all squared, but that's just 2i. And then ci plus d times 2i. And then real part must equal real part, imaginary part must equal imaginary part. So c is 0, d is 1/2. I've still got to work out a, but I know what b is, I know what c is, I know what d is. So I'm just going to sub in x equals 0. And then I should get something fairly simple. I get left with 2a, and when I substitute in the b and d that I've already worked out, I've got that a is actually just equal to 0 for this one as well. So my integral becomes -1 on 2 x plus 1 squared. So that's to the power of -2, so we'll just add 1 to the power over the power. And then we've got x squared plus 1 with a constant on top. That's going to be an inverse trig function. So we have, well, I've changed it to index form. And so add 1 to the power over the power is the -1 over -1. The second one became inverse tan. I factorised out the common factor of 1/2 there, you'll notice. And so I end up eventually with 1/2 outside of 1 on x plus 1 inverse tan x. Now, there is another way of finding these constant values, which some people call the Coverup method, you might have noticed. So, first of all, the idea that most people get shown is this. It's just when it's linear factors. So if I've got a on x minus a, b on x minus b, c on x minus c, and we know that's equal to some function on the top of the fraction, and there's all the bottom. If I want to find a, I substitute a into this expression. Why the reason it's called cover up is an easier way of thinking about it is I'll cover up the x minus a, and then I'll substitute a into everything else. And so I get function a over x minus a, a minus b, and a minus c. And that'll work out the constant a. And if I want to work out the constant b, well, then I'll cover up the factor x minus b and substitute b into everything else. So function b on b minus a, b minus c. And if I wanted to work out c, well, the factor is x minus c, so cover up x minus c, substitute c into everything else. So let's just, and so on, if there were more, we keep going. So let's have a look at the ones we did earlier, just to show you that idea. So here we are. If I want to work out a, I would cover up the x, substitute in 0, because that's really x minus 0. You're basically saying what makes this equal to 0. And that's what you're substituting in. So 0 would make that equal to 0. Sub that in, I get 3 on negative 1, which is negative 3. If I want to work out b, I'm going to substitute in 1, cover it up. 3 over 1 is 3. There's b. This was the next example we had, so same again. If I want to work out a, I'm going to have to substitute in 5, because that's what will make x minus 5 equal to 0. Cover it up. We'll have 5 plus 5 on 5 plus 2, 10 on 7. Want to work out b, now I'm going to sub in negative 2, because that's what will make x plus 2 equal to 0. Cover it up. Negative 2 plus 5 over negative 2 minus 5, minus 3/7. Okay. Now, as I say, people only seem to use this for linear factors, but there's no reason why this idea can't be spread to other more complicated factors. So I could use complex numbers to do the quadratic factors. Because those quadratic ones, the reason they say, oh, it's not linear, I can't do it. Well, I can, because all we're really doing is to say, what do we substitute in to make this factor equal to 0? If I use complex numbers, I solve the problem. So the next one was here. So if I want to work out a, I'm going to substitute in 0. So cover up the x. I get 1 on 0 plus 1, so it's 1. If I want to work out for bx plus c, I'm going to substitute in I, because that's what makes x plus 1 equal to 0. Cover up the x squared plus 1, and I get 1 on I. Realise the denominator is minus I, and then real part equals the real part, imaginary part equals the imaginary part. So it still works. Here's the next one. Oh, actually, I don't think we did look at this one. This one I just threw in there to show you that the idea works, because we've got a couple of factors here. To work out the a, I would substitute in 1. So cover up the x minus 1. It'll be 1 squared plus 4 over 4 times 1 squared plus 1, which works out to be 1. To work out the bx plus c, I have to ask myself, what would make 4x squared plus 1 equal to 0? Well, the answer to that is a half I. So I'll substitute in the half I, cover up the 4x squared plus 1, so x squared plus 4x, subbing in a half I, and then x minus 1 on the bottom, half I. Tidying all that up. There's a little bit more work to do, obviously, with that one. And maybe that's why people don't tend to use it for quadratics. They think, oh, too hard. Yeah. But it works beautifully. We get 1 minus 3 on 2i. Real part equals the real part. Imaginary part equals the imaginary part. So b equals negative 3. C equals 1. What about if you've got multiple factors? It will still work, just requires a bit more work. So we have one like this where we had a double root at minus 1. All right, well, a is going to be easy enough to work out. Cover up the x plus 2, substitute in negative 2. I get negative 2 for this one. Now, working it out, it's the highest power you work out using this method. So it's the x minus 1 squared, so it's the constant c that will work for this method. So if I cover it up and substitute in 1, that will work out c for me. And c is 3. So what I now do is just go, well, okay, I just do a clever substitution to work out the missing pronumeral. So x equals 0 is nice and easy. Let's just sub x equals 0 into this expression. And we know what a is, we know what c is, so I can work out b. Okay? So it's the higher power. That's the constant you'll work out using this method, and then substitute back in something simple to work it out. All right, let's have a look at this one, where I've got a quadratic, I've got a multiple root, and I've got a linear root. So, okay, B, I'll substitute in -1. Okay, that'll get rid of the higher power. So that's why I couldn't work out A. So B, it'll work out, it's the higher power. Sub that in, covering up the x plus 1 squared. I get -1 on -1 squared plus 1, -1/2. Now I'll go work out the cx plus d. I can do that using I. Substitute I in, cover up the x squared plus 1. I on I plus 1 squared. I plus 1 squared is just 2i. I's cancel. It's a half. Equate the real and imaginary. So I now know what B is. I now know what C is. I now know what D is. A simple substitution will work out A for me. So let's make x equals 0. Subbing it in, we get A plus B plus D is 0. And so A turns out to be 0. Well, what about a quadratic denominator that theoretically can't be factorised? I mean, x squared plus 1, theoretically, can't be factorised. We use complex numbers, but we can do that for any quadratic. X squared plus 4x plus 5. Right? It can still be solved. I've just got to use imaginary numbers. Remember, the idea was what makes it equal to 0. So A, nice and easy. I'll just sub in -1, cover up the x plus 1. Now, x squared plus 4x plus 5. What makes that equal to 0? Well, if I'm not sure, let's complete the square, and it'll be a bit more obvious. This becomes x plus 2 all squared plus 1, so it must be 2 plus or minus I. I can use either one, it doesn't matter. I could use 2 plus I, I could use 2 minus I. So, oh sorry, -2. Whoops, my mistake. Of course, x plus 2, -2 would be the solution for that. So -2 plus I. Yes, it might involve a bit more, but remember we're covering up the x squared plus 4x plus 5. I'm just substituting it into the x plus 1. So I have -2 plus I plus 1. Realise the denominator. And what have we got? Equating real and imaginary. With imaginary, B is nice and easy to work out. It's -1. The real part is -2b plus C. And so from that, using the answer I just got for B, I can work out C as well. So all right. As I say, that's a cover-up method, which some of your tutors might have shown you the simple way of doing it for linear factors and said this is all it works for. Guess what? They're wrong. Mr. Simmons is right. He's more clever. Okay, so here's the ones that we got for partial fractions here.